Hi, Martin.
Hi, how are
Oh,
you?
yeah, not too bad. Not too bad. It's getting better weather again, or at least warmer. It's still a bit rainy, but
Oh yeah, we had some really nice weather last week. It was like almost summer-like.
yep. Hi, Shane.
Hello.
Oh,
Hi, guys. Okay. Check who's there. Und
you're funny.
ah.
You added my topic, but you didn't add me.
Oh, yes, I forgot. Wait, I do it quickly. Uh, d-
Hi, Shane. Hi, Derek.
Hello.
Thank you. Hi, Steven.
Hello.
I think we're complete.
Awesome, that looks good. Give me a second. Oh, and the chat. Okay. So, hi, everyone. Let's get started. And also, by being here, we all agree to the GraphQL Spec Membership Agreement and to the GraphQL Foundation Code of Conduct, which all are linked here. So if you want a refresher, you can read up on it. Let's do a quick round of introduction in the order of the agenda. My name is Michael, and I'm the host today.
Hello, I'm Shane from Apollo.
I'm Martin from Apollo.
I'm Sachin from Apollo.
Derek from Apollo.
I'm Steven with Netflix.
Papa to the screen.
Awesome. Let's also quickly look at the action items because I added them. And we had this enable AI summary, and we are working on that for the notes. And this, I hope, will make the note situation for this working group better. So we have the legal okay. I got it today, but we haven't yet been able to activate it in Zoom. So we are already using it for the governing board meetings, but it's not activated at the moment for each workgroup meetings. But I think we get that worked out with the Linux Foundation account in the next couple of days. So hopefully next meeting we have an AI assistant taking the notes. Anyway, so this is this ongoing, and will also be done as far as I know for most. And now So the comment every I tried asking ChatGPT to write the spec is not yet there.
But it at least helps with the wording. You still have to
Yeah.
write it, but it makes it at least.
It's good for corrections, right? If you want to check if the language style or is good and for spelling.
But it can't do algorithms. It just doesn't understand the format of it. It always so annoying. Anyway,
Yet, yeah. Awesome. So we have one topic so far on here, which is that we circle back to satisfiability. I mean, we have a couple of things in the pipeline for writing spec text, but discussion-wise, we could finally start again on satisfiability and look at how we structure it, how we want to formulate the algorithms in a way that the spec doesn't become too complex, but also in a way that there is spec text that describes how you can implement it. If there are other ideas on topics, shoot now, and I put it on the agenda.
15 minutes seems very optimistic.
Yes, I just wanted to suggest there's some space for something else. But if there's nothing else, there's anyway, we have an open-ended discussion.
yeah. So I can show you some notes. Let me copy this quickly over into code.
Should I stop sharing?
Well, if you want that I share, then you have to.
Yeah. Yeah, I just always, I think it's helpful with the agenda because before always we struggled who is next.
So this at first this will be a bit of what we have discussed already before, but I believe what's happening now at the moment in the spec is I'm working on resolving the 56 issues that we have open. I already have a pull request open which resolves a few, but there's a lot more spec work to do. That's the reason why we haven't like moved into on satisfiability a bit further. But this meeting, I would say, what we should do is to just brainstorm a bit. What do we even want to have satisfiability do in the spec, right? Because when let me share the screen quickly. We can even either have it in, so one extreme is that we have it in algorithmic form. The other extreme is that we essentially just say is satisfiable true. And we just describe that the schema has to be satisfiable. That's obviously not what we want. We probably want to go more into the direction where we have spec text that actually explains exactly how satisfiability could be done. And the question is a bit if we can break it down to a level of rules, like similar to what we have with the satisfiability with the validation, or if it needs to be in a different structure. So at the moment, I would say what we should find out today is a bit how do we want to specify it, and then we can work on a draft like how the specification could look like. And we did already a few months back, we had already a discussion about satisfiability and then reiterated over keys and whatnot. So it's an open discussion to how we could specify it. There's one, there's also we could, in the end, it would be nice if we would have an algorithm that you could follow to verify satisfiability. But it's also a long shot. I'm not sure if it's even possible to do.
Yeah, it doesn't necessarily have to be inefficient.
Yeah,
algorithm?
that's one thing. One rule for satisfiability is this will be endlessly optimized in the implementation. It's like the validation rules in the graphical specification, right? No graphical implementation. I'm not sure if graphical JS does it, but all of the high efficient graphical implementations do graphical validation completely different from what it is written in the spec. Just because the spec is written in a way that should be human understandable, and the machine could execute much faster. So we have to get rid of the idea that we have a complexity problem. We can visit the whole graph theoretically for every field not unlimited times, but multiple times. Like if we have rules per field, for example, we could, I'm not sure if this makes sense, but when we say that we want to execute a rule per field, and this rule would have the requirement that we visit the whole graph to find if it's really satisfiable or not, that's no problem at all. From a specification point of view. If it helps with the understanding, we don't have to worry about algorithmic complexity or just in general complexity. So this was an initial draft of at least 2 rules that we know the Federation has at the moment. So I believe when you're in the satisfiability can fail with cannot satisfy required conditions, and there's probably more around this. And another one would be insufficient key fields when you cannot do the transition move, or however we want to call it, between two different source schemas. And when we do it based on rules, we can have it similar to the validation, where we have a title, we have the error code, we explain, and we have examples where it shows what's an example and the counterexample, what's satisfiable and what's not satisfiable. If we go with this, it would be really helpful if we get more than the set of 2 rules to find out what we actually need to validate. And when do we do these validations? Are these validations on field level, on type level, on subgraph level? That's one thing that we have to find out.
And to be clear, where do these rules come from? Are these things that you wrote up in the process of thinking about this?
I believe so. As said, I've just searched my Obsidian for satisfiability and stumbled over this guy, but
Yep.
also stumbled over this. And it's also the notes that we did based on the discussion that we had before. So this is, for example, satisfiability, or that it can have cascading errors. We have override. We have an example.
Yeah, these are the
I
notes
think it might be
that we did last time when we discussed about
okay.
about it.
Yeah. No, I was just wondering, it might be helpful to take a step back and try to sort of formulate the property we're trying to establish here.
Yeah.
And
yeah.
then these rules, it makes a lot of sense to have sort of specific examples. But in terms of rules, these seem like very sort of local rules. And I think the way we've formulated satisfiability, these are usually more like path dependent rules. Like for instance, the no key field. I mean, there might be one path where you're not able to jump to another subgraph, but you might still be able to satisfy the field because there's like a completely different path to the same field. So I'm not sure if we can actually formulate these rules in terms of sort of local rules.
Yeah, we could. I mean, that's completely fine. I mean,
It could also be that it's formulated in a path-finding algorithm style of thing.
Yeah. And to be clear, I think we're all very open to thinking about alternatives. But I think it's important to sort of establish the property we're trying to to check here. But the problem with that property is that it's a very global property, and that leads to algorithmic complexity. So if we can find sort of easier ways to specify constraints at a sort of more local level, I think that would be great. But let's see sort of how we can get there.
how do you do satisfiability at the moment? Do you do it with a graph finding algorithm where you traverse through the whole set of possibilities on a field level or on a subgraph level?
Maybe
Yeah, Sachin might
first,
be, or yeah, or
maybe first, Martin. Maybe you should specify the fundamental rule of federation that we established, because I think that's where you wanted
yeah,
to like kick this off, right?
sure, sure. So the property we're trying to maintain here is that basically any valid query against the API schema, against the sort of public API um, that sort of is exposed from the supergraph, we have to be able to um, satisfy that query in terms of subqueries to subgraphs. So there has to be for every sort of valid GraphQL query that you can formulate, there has to be a way to get the data for those fields. And that sounds sort of simpler than it is in reality because there are many situations, especially when you think about like abstract types and shared fields and ways you can traverse between subgraphs. You do get into situations where there are many possible paths to satisfying the same field. Um, but I think Sachin probably has the best understanding of our current algorithm and sort of what we've done there to optimize things as well, possibly. Um,
Yeah, that's right. I can maybe speak a little more to that. I won't talk too much about the optimizations just because there's a lot of them. I'm probably gonna just maybe try to talk at a higher level to start with, and we can maybe dive into optimizations as people have questions. The gist basically is we consider satisfiability as thinking about paths, right? So you think about possible paths you can make on a schema, right? So between fields basically or inline fragments along the path. Um, and the answer is basically we basically try to make sure that for every possible path you have, that you can formulate some sort of subgraph queries that will get you there. Is the idea. That's sort of the first simplification. You don't think about generic queries. It's just only one element at a time as you're going through. Um, the other thing that's a bit simplifying here is that we have some basically a form of loop detection, right? So we keep track in the sense of like there's points basically where you can sort of prove that because you've already reached the state you're at before, you don't have to continue iterating, right? So this is how you get around the sort of the infinite query problem, the infinite depth problem. There's ways to keep track of sort of have you been at this location with the same state before, and if you have, then you can sort of avoid recursing further, and that's sort of the other half of why it's able to sort of do it in a finite amount of time. You state that it's kept kind of, it largely depends on what features are sort of implemented in Federation. As we sort of add Federation features, we often find we have to change the exact state that's being kept track of there. As an example, you keep track of the nodes in a query graph in this case. Different paths you get to that node, as an example, and then you can use that later as you traverse. But that's maybe too in the weeds. I won't necessarily go too far into that. But that's sort of the gist as a whole. Is it basically looks at paths on the API schema, and then it tries to detect when you have a loop so that it doesn't traverse any further than it needs to. And then once it's essentially iterated through every possible path, it stops. If there are any path that defines that it can't satisfy, it'll emit an error. And it generally tries to keep track of like if there are reasons why it couldn't make a traversal, it'll keep track of those so it can sort of emit them later if it finds out later that it has no options. And that's how you get the error codes today, basically. But that's the story there.
Okay.
And maybe just to, I know we're all GraphQL experts here, but to really specify everything, what is a path in your mind?
So a path in my mind basically is basically a series of consecutive elements, right? So you can think of a GraphQL query as basically like there's a top level field or a top level sort of element, right? And this element in this case is basically either a fragment, or in this case it's imaginable, or I guess first off that you've sort of expanded fragments, right? So expanded name fragments. There's no longer any named fragments in your query. Just for simplicity's sake, let's consider that. A path in this case is basically a series of elements where each element is either a field or an inline fragment. To be clear.
But it's
So maybe I can type it in Zoom chat or something like um,
You can also share the screen if it's easier.
but it's
this for example, or
yeah, but it's also like when you consider these passes, right? It's also you have if we like not every type is an exit point. Or to pick up the terminology that actually Martin brought in, like there are types that might not even be mergeable as top level type where you can jump off, right? So these you could already take out of the traversal.
well, I mean, these are paths on the supergraph, right?
Yeah. So these kinds of paths are things where like they are on the API schema or the supergraph schema, and then there's a separate question of how you actually end up planning those. So like as you're going along in our case, like we look for different like possibilities for each one, and it's true that in some cases you have some types that actually are nodes, in this case they aren't exit points, so you can't actually take those. But you basically try to find the things that you can reach basically. And that sort of determines that. And then we basically track it for each node in the query graph. A path that essentially reaches that node. It's a little more complicated than that again, but we'll just for simplicity's sake say that.
Yeah.
Yeah, so paths have nothing to actually do with the subgraphs or plans themselves. They're just saying for every possible query, every possible way I could query maybe a particular field, or the paths I could get to that through a root query mutation, through
Yeah.
all the different things. What is I can get here this way. Every path has to have at least one valid possible query plan we could generate.
Yeah. And
That's
let's
correct.
so let's say you have a name field on a user. You might be able to get there through a user by ID root field, but you might also be able to get there through like top posts author name. That would be a different path of getting to the same field, but that whole path is important for our ability to check satisfiability because it might limit sort of how you can get the underlying data from subgraphs.
And if the state that you have in a graph, when you said that you know the infinite loops and so on, this would be the state that you have is essentially the are these the arguments that you passed in to the operation. For example, when you have to get
It, it's not really the argument you pass from operation because this is a composition of time, so you don't really have the arguments or any values for those things, right? By the state, I mean things like you could imagine keeping track of for each how to say you can imagine keeping track of for each node in your query graph what paths to get that let you get there, right? So if you keep going and you reach the same node later in the future, and you haven't, if the number of options you have to have gotten there have not strictly decreased, then essentially you can say that you have essentially reached a loop, right? That's sort of the more confusing, or that's I think the most complicated part of like thinking about that particular algorithm. Is basically you think about the possible ways you've sort of taken to get to a particular point in the query graph, and you keep going, and eventually if you reach the same node later, and the number of ways you've taken to get there has not decreased, then you can say that essentially you can continue going and you still get the same thing, is the idea. So it's maybe a little more it's
Sachin,
abstract.
I think you're talking about the optimizations that are made to actually not do extra work. But in the end, what we're talking about that for any leaf field in the graph, there has to be a valid path to get to it on the very high level, right?
Right. I'm talking about more about how do you avoid like situations where, because essentially you could have infinitely long paths in this scenario, or like arbitrarily long paths, I should say, right? And so like the
Sure.
problem is you can't obviously can't test all those arbitrarily long paths. It's infinitely long. So there's essentially code to make sure that when you've essentially reached a point where you can prove that you would essentially keep looping in some sense, you can
Yeah,
stop.
but it's you want to avoid the cycles, but it's like you still have the the leaf nodes there, but you can go through one, but you're not gonna be going through the same cycle
Yeah.
many times.
But I think avoiding cycles should probably be a property of the high-level algorithm as well. I wouldn't just consider it an optimization.
well,
Cycles are pretty fundamental.
Yeah, it takes infinite time if you don't cycle detection.
Yeah.
Cycle detection is much simpler than optimization, right? Because cycle detection is essentially if you reach a field through the same path that you have reached it before, like from let's say from type A to B to C back to type A, B, C, as soon as you reach it second time in the same hierarchy, you know that you don't have to validate any further, right? Because you're in a loop.
Not necessarily,
It kind of depends. So
unfortunately.
if you have, yeah. So basically, there's also this notion in validation for particularly considering this notion of like some state can be considered a substate of another state, in the sense that like if you've reached a state which is a super state, then basically if you have a state where you have the same more number of options you did before when the last time you hit the type, if you keep going, you can always still find the same number of options because you could just limit yourself to the options you had before, and you'd end up being fine. It would be inverted. Sorry, I have to look at the algorithm again. Maybe I'm saying that inverted. But I think that's probably the more that's essentially how cycle detection works today. Is it sort of looks at the options you sort of have to reach a node as you're going along, and it keeps track of those for each time you visit a node, and then it examines your prior options. One second, let me see if I can take a glance at the code real quick. But um,
Yeah, but I think it still brings the question from Pascal of how we want to document it. Ideally, that would be around like we have X amount of different rules, same as for like composability stuff, right? And you have to basically ensure that those are there, so it's actually easier to understand. At least that's what my preference would be. But if we can try writing the more general algorithm without those validation rules, but it would be nice if we can actually slice and dice it into those chunks.
Yeah, but I don't think those rules by themselves would be enough. But we still need to specify the high level algorithm, like how we construct paths, and,
Yes.
etc. But those rules might specify how we traverse, for instance, from one subgraph to another. I think that's an example of a rule. Like you need the keys, you might need require arguments. I think those are all things we can specify as rules.
I mean, it's probably sorry, Shane, go ahead.
That's why I wanted to maybe step back, because I think we can talk all day about the planing algorithms. Maybe just because we haven't specified it, I think we all understand the fundamental rule, what paths are. Maybe just to clarify again, in the current Apollo Federation implementation, what are the inputs to this satisfiability? We are only looking at the supergraph schema, or do we also consider the composite, the subgraph schemas themselves, source schemas? And then what is the thing that like we iterate over? Are we like going to like for every leaf node and we start there and we look at a leaf node, or are we just like, do we like just generate operation? Like more generically, like what is the thing that we like iterate over?
Yeah, so
with inputs.
one thing that we specify, just to cycle back on that, is that we don't specify the supergraph format. We can specify what data we need, but there is basically in this spec no supergraph format itself. Okay, sorry, you can go ahead.
We do have an API schema, right? That's the public facing one. So basically any valid query against the API schema is the one that you do. But
Yeah,
that's how you use the supergraph to basically do the joins and all that stuff.
and for us, the supergraph format actually contains like all the relevant information from the subgraphs. So in terms of like this spec, we can just specify that we have like the subgraph schemas available.
Yeah. Internally, essentially what happens is we take the supergraph and we decompose it into subgraphs, and we use that to generate our query graphs, and then we do the algorithm. So essentially it is on the subgraphs. You can consider that, and then we don't have to talk about a supergraph format or anything like that. If we just consider on the subgraphs, then that's fine. I found the line that I was looking for, specifically assigned. So I did say it right the first time, but that's a line essentially that's responsible for loop detection, for folks who are interested. And there's a comment there that sort of explains it a bit more. Basically, you're keeping track of possibilities and ways you can reach a thing, and if it ever shrinks, that's a problem. But if it grows, it's not really a problem. That's when you stop the cycle, basically. But yeah.
Is it from an algorithmic point of view? Is there some known pattern that you do for? I mean, out on top of my head, it's probably is it? Do you do DFS until you find something? Do you do BFS? Because we need a way how we can describe what we do over all the fields. We cannot just have the rules, as Martin has said. We need some algorithm which explains how we traverse the graph. And now the easiest or the most known ones is just you do a BFS, a DFS, and then you can traverse all the graphs of a node. All the nodes of a graph, the other way around. Is this also something that you use this obviously optimized in your implementation, but is it at its core one of the simple algorithms like BFS, DFS, and so on?
At its core, it's kind of like DFS in some sense, because what you're doing is basically in your query graph, you have you basically can take fields in a type, and you can take inline fragments of another type, right? Or you can essentially take a type condition inline fragment to another type, right? And that's kind of what you iterate through in this sort of DFS. Basically, for each type, you go through every field and you go through every type condition to a object type, basically. Is the idea. Yep, yep. You don't necessarily go to all the types because technically, like when in GraphQL, you can always put anything in a type condition as long as there's some non-zero intersection. So that's a lot. So this is just one of those optimizations. We only consider going to object types, and basically, we make sure our query planner is such that as long as you do object types, you can do any type. So that's more of an optimization talk, but we don't necessarily go to every type condition. It's just
But
type conditions.
there's every field,
Yes.
every possible type with some optimization, of course, but also kind of subgraph based, right? Because
Yeah.
you could be on a subgraph and cannot leave anymore. There could be fields that you cannot resolve in certain conditions, right? Like
Right.
when you reach I don't know, a local maximum and you cannot go any further, then
That's right. At that point, you would find that that path in the API schema is unsatisfiable, and you would admit an error for that. That's the case, right? So, like, if you keep going along these paths and you find a path where, like, this basically does this DFS through these paths, right? So, like, you can imagine adding more and more as you go along to a given path, right? And as you're doing this, you can find that actually there are no options left for to resolve a particular path, right? Because there are no subgraph jumps, right? Or maybe you've reached an exit point which doesn't actually have any exits or something of the nature. In which case, you would
you just
I think it might be helpful to clarify what we mean by option here.
Yeah. An option in this case basically is a path or potentially a partial path through the subgraph schemas that satisfies a particular partial path in the API schema. So by partial paths, I mean a path that doesn't end in a leaf field. Because we're iterating through and through this DFS, we're iterating through partial paths of the API schema, and we are finding partial paths in the subgraph schemas to satisfy those partial paths in the API schema.
Okay. And yeah. And you, for each field, you essentially need, you just validate that there is one way to resolve it. And you have all the possibilities of moves, of jumps, whatever we define with lookups. You just need to satisfy that in the current context, all the fields on a type. Let's say I'm ABC, I'm on type B. My path is query A, query, field A, field B. Now, what I need to verify is that C is resolvable. And I only care about one case where this is resolvable. I don't care if I need 7 jumps in between. It just needs to be somehow resolvable.
Right. It's true that you don't technically need to care about all the options that you can use to reach, like B, for example, when getting to C. But you need to keep track of the options for each node, right? So it's possible you have a type B, but the B could be across multiple subgraphs, right? And so you need to keep track of essentially for each subgraph a path that gets you there if it is available. That's essentially what I mean when you look in the code, there's like this notion of a collection of paths for each node. That's basically what's sort of kept track of there. Is we keep track when we're going along these partial paths, we don't keep track of a single path to reach that. We keep track of a path for each for a type across each subgraph.
Right.
Yeah.
Because basically later you might need those paths or need to traverse from a different node in the query graph.
Yeah. So if, for instance, if in this example you have not just field C, but you also have field D on let's say type B, then those fields might actually come from different subgraphs or be reachable by like entirely different paths through the subgraph.
Right.
Okay.
Yeah, you don't need to keep track of every possibility, but need to keep track of a possibility per node. Although, again, this becomes more complicated if you add more federation features that maybe make it path dependent. And I won't get too much into that because that's a bunch of complicated features. But
it's actually not. It's actually not just that you traverse the query. It's not that every leaf field of the supergraph needs to be resolvable. It's actually every leaf field of the subgraph needs to be resolvable.
No, the starting point is always the
supergraph.
the API schema, the supergraph. But you do need to keep track of the entire path. Like it's not just talking about like leaf fields of particular types. You also need to keep track of the path that took you there. And in taking a specific path to a leaf field, if you're thinking about possible ways of satisfying that query, that might lead you to very different paths through subgraphs. So you also need to keep track of those, and that's what we call options.
Yeah, and in this context, that's what we refer to as options. Basically, we keep an option per subgraph, comma type. Yeah.
Okay. And this is for all the places where you have multiple options that you go. So when I can resolve field C from subgraph A, from subgraph 1, 2, and 3, then I essentially have to check the type C for these three options. I have to check it. What happens if I go first to subgraph 1 and then try to resolve a field? What happens when I go first, I go first to the subgraph 2 and try to resolve the fields and so on. So as soon as you start, when you have multiple options, you have to verify all of the options in this context.
Right. So it's worth knowing that we don't necessarily need to think about all the options that can reach a particular node in the query graph, right? So like if and by node in the query graph, maybe I should more specify. By node in every node in the query graph in our case, and at least for now, I'm changing in the future maybe, is identifiable by a pair of subgraph name, comma type name. Today. That changes in the future, but I won't talk too much about that. But today that's the case. So the idea is basically for each, and when you're at a particular type, you need to basically have a path for each subgraph. You don't necessarily need to have one. It's possible you couldn't find one, but you need to keep track of those basically. And that way, when you go to the next field or the next thing on that type, you use those paths you already have, then figure out, okay, for each of these nodes across each of these query graphs that represent this type, can I to actually take this field or reach this field C? If I was at B before. If that makes sense. And that basically means that for the next, after you make that jump from C or essentially add C to your partial path, you have a new set of nodes, or a new set of paths, I should say, for each subgraph.
Do we need, is the partial path thing an optimization that you did to do less visiting?
I mean, the partial path
is there a common set of rules that we have when we have to, like, the options make sense because you have multiple options how you can traverse a graph. Now, from an algorithmic point of view, we could define this as part of the traversal, right? Like for each graph, do whatever. For each subgraph with this type in this, in this path, whatever, we can do something. And we don't have to worry about complexity, algorithmic complexity. We just should try to make it as simple as possible in words how we can do this. And yeah, we may need to identify a bit what we have to do during the traversal to then bring it on paper. So when I visit this query, let's say I have a supergraph schema, what's the first thing I do when I execute the satisfiability for the schema that the query that, or the schema that we have here, where the query ABC is executed?
Right. So in this case, you would essentially suppose you're iterating the DFS to the API schema's query graph, right? So the API schema itself technically has a query graph in our case, and so you eventually come upon this partial path that's query ABC. There could be again more fields after D, but let's say we got
how do we one second how do we get, I start satisfiability. I have a supergraph schema.
Yeah.
I don't have a partial.
We start from the query root, and then basically we look at every field, and then at the return type and every possible field of that return type, et cetera, et cetera. But of course, when there's an abstract type, we have to do that for every possible object type.
Right. It's a DFS to the query graph for the API schema, basically. So like, if you imagine the API schema, when I say the phrase query graph, you can think of it as the nodes as types and edges as basically either fields or inline fragments. You can imagine traversing that graph in a DFS-like fashion, starting from the root operation types. And that's basically how we create these paths, or essentially iterate through these partial paths, is by doing that DFS.
So in terms of sort of how we could describe this in the spec, like one way of approaching this would be to start with just a way of generating all possible paths from an API schema. And that would give us basically a list of possible paths. Because like as part of our optimization, we try to keep these partial paths and we have sort of state we keep in there. But all that I think we can leave out of the spec text. So the starting point for the spec text is just a way of generating all possible valid paths from an API schema, I would say.
Yeah, it's a good starting point.
When we look at composite types, And I mean, like object types, union types, or whatever as a field output type. We look at all possible casts in a way, like because when we are talking about fragments, it's not only just like when I look at an interface or all possible paths in the sense of the GraphQL spec, which would just be object types. We look at all possible interfaces and abstract types that could be in this place, theoretically.
Right. So that it's definitely true that in GraphQL you are allowed basically for a type condition to have any type in that type condition as long as there is a non-zero intersection between the type condition and the parent type of the inline fragment, right? So as long as like the runtime types of them match or at least have some overlap, you can have that. But in composition, basically as an optimization, we only look at the object types because in our case, at least for Apollo query planning, that as long as it is true that you can do it for the object types, you can do it for any other possible combination of any other set of types.
Yeah, why I asked that is because the abstract types could also be on some subgraphs, but not on all, right?
Right.
So depending on the fragment that you formulate, it could be that it forces you to a certain subgraph.
Well, so in that case, we have the thing called type explosion, right? So like what happens is if we see a type T that doesn't exist in a subgraph and we notice that, hey, that T doesn't exist for some, there are other reasons why we do type explosion, but this is one of them. If you notice the type doesn't exist, you can break it into its constituent runtime object types, which it supposedly should know about, and know about some of them at least. And the ones that it does know about, you can do queries against that. But that's essentially what happens in Apollo query planning today, is if we have a if you have a abstract type in a type condition on a subgraph that doesn't know about it, essentially it is split into its constituent object types, and the ones that it does know about are made against that subgraph.
Okay.
So.
Okay.
Okay.
To go back one step again, we generate all possible paths. A path is always query route to a leaf field. It's
Restart.
Yes. Complete paths would always end at a leaf field. I think.
We call those closed paths, but yeah, complete paths also.
Yeah.
There's open paths and closed paths, and open paths are ones that don't end in a leaf field. Closed paths do.
Are open paths part of an optimization or part of a requirement?
Yeah, it's an optimization.
It's an optimization. Yeah, I don't think we need to concern ourselves with those for the spec.
Okay.
Yeah, it technically isn't necessary to formulate the spec, but if you wanted to actually like write this algorithm in a way that didn't take infinite time, you would need to probably have some concept of them as the thing. Maybe that's the one caveat.
Yeah,
right?
but that's completely fine. And the people which implement this have to figure it out.
Yeah.
Yeah, but so we will have nodes. We will have non-normative nodes there and explain, okay, here you probably need to have optimizations.
It's also good because if you specify it too closely, everyone will implement it. But if you specify it openly, everyone will implement it slightly different, and that will lead to the optimization in validation that we see in GraphQL Java, where this validation suddenly is 1,000 times faster than it was before. So it's also good that we don't like force people in the specification into having to do it in a certain way as long as the outcome is the same.
Yeah, and then what's nice about this way of describing things is that basically each closed path can be checked in isolation. Like we're basically restarting the whole process again. Like
yes, exactly.
So what we're doing is we're just generating like every possible closed path, and then for each path, like just in terms of like the way the GraphQL spec is written, these can be separate functions. There's just a function that takes in a closed path and checks like whether that path on the API schema can be satisfied through this collection of subgraphs.
And the generating all possible paths essentially would also do the loop detection, right? That's part of.
I think we would want to describe that there. Yeah, similar to how you keep track of like visited fragments or something in the GraphQL spec.
Yeah, so that would be the part of this would be the loop detection, and we get out and not an infinite amount, but a finite amount of paths. And then we could run the validation based on these paths. So let's say we have generated all the paths in the spec, and now we get the query, the query path, query ABC.
Yeah.
Now we have a function which can validate the satisfiability of this specific path. That's very good, because now we have just broken down the whole complexity into something which is just a slice of complexity. Okay. And what do we do with this query path when we start? Let's say we have the input of the query path, and now in a very simple way, we have to verify that this is satisfiable. What are the steps that we have to take to make sure that this is satisfiable?
So the gist today is basically we're on a simplified version of Apollo query planning to some extent. There's a lot of sort of things I'm omitting there, but that's kind of done in that fashion, and it uses the results of previous open paths to sort of speed that up, right? But that's kind of, you can imagine what the story is today is basically for each closed path, you can imagine just running query planning on it and seeing, does it generate a option? And if the answer is it doesn't, then, then basically that fails, right? But we just happen to keep these optimization as open paths, so you don't essentially have to like redo it every time.
Right, that's interesting. So you run on the path, you run the query planning.
Basically, yes. The thing is, it's iterative though, in the sense that it uses a previous state that you have to sort of speed up that query planning. Like
Yes, but
conceptually,
that's something that we don't care about, because
right.
that's, I mean, we do obviously in implementation. I'm not just trying to say something wrong here, but in the specification, because one thing that we haven't talked about at all, and one thing that we need to define is the execution behavior of the supergraph. Let's say we don't have a format, but we need to, once we have a composed graph, we also need to define how do we actually execute this. And here we can make a really easy shortcut in satisfiability, because I agree, we generate these query paths, we have all possible query paths, and then we can just say that all of the rules that we have in query planning, or that there needs to be a valid query plan for this, and we can just refer to the execution section where the execution happens. And now we actually have a very clear definition on how satisfiability works. Is we have these query paths, and we start the query planner on it. And if the query planner succeeds, then the schema should be satisfiable. And it's very clear in the execution how we what's satisfiable and whatnot.
And I think for understandability, it's also really nice that we can actually write these paths as queries. So it's basically saying you have a query that results in just a single field. And that's what we're planning against.
Yeah, it makes it a lot easier to think about for a user, because then they can say, oh, this query doesn't work, and we can explain to them why it doesn't work, because there are certain subgraph jumps you can't make. And it's a lot simpler if you have like a simple example that basically a counterexample to why their schemas can't compose, basically.
Okay. Now, that makes things easy, because the query planning is a completely different chapter where we can do whatever we want.
Yeah, I do worry a little bit that we can't really define the loop detection without thinking about the open path and the like of state and whatnot. That makes me a little worried, but maybe that's something we don't have to think about now. I'm not sure.
But
it's also something we can iterate on. Like once we have the first spec text and we have a simplified version first, we can also look at how we could integrate such a thing.
I have a question about the loop detection. Why isn't it enough to just see if you have visited, if you look back, like you're visiting, you're generating queries, and then you see that you have the same type sequence twice? Why isn't this enough to detect the loop?
So it's possible that you may have reached the same type as you've done before. And so you might have processed the type before, but you have less ways to get there across subgraphs. For example, like before, when you reach a type, you actually could reach 3 different subgraphs with the type. And you reach the type again, and all of a sudden you can only reach 1 subgraph, right? It's possible then if you keep going and like keep adding whatever thing that gets you back to T, you might end up finding there's 0 types, in which case it's an unsatisfiable schema, if that makes sense.
Well, Sachin, what we just said though is for the more simpler spec text, we shouldn't actually really care about subgraphs per se for the generation of all query paths, right? This is just purely look at your API schema of the supergraph. There's no metadata even. We don't even necessarily care about that. And we just say, generate all possible queries. That's what we're doing, right? And so the loop detection there should just be, if I go to, enter through user and I get the reviews and I go to the author and that's back to user, like the path of,
that doesn't work, to be clear.
User dot other.
Like you can't just say that once you've reached user again, because I visited user before, that's a loop. It has to be something that is aware of the path you took, the possible subgraph path to take to get there, is what I'm saying.
Yeah, so
Right?
it's
Oh,
not
so
it's not just the type.
loop.
It has to be the
Okay.
fields of the path through the fields I got to the type, which is repeated. But if that field path of, query dot user dot reviews dot author, so it's user dot reviews dot author, that field path is repeated, then we can say we visited that
But it's
that
not
section
only
again,
that,
right?
right? As far as I
Yeah,
understood, it also has has to have the subgraph context in
right.
there. Like
100%,
Yeah.
right. Yeah. Basically, in order to detect loops, you need to keep track of the actual paths you can take in the subgraphs to reach that type or that API path basically that you reached before. And that's sort of the thing there. That's why I'm saying loop detection basically kind of requires you to think about the subgraphs. Is the thing.
Okay. When we talk about passes, it's not just the type pass if we think in a unified schema. It's actually the pass to this field through the various subgraphs that we took.
Well, not directly. Like we're still talking about like a path at the API schema level. It's just that like if you take a certain path to a certain field on a type, that restricts sort of the paths you can take through subgraphs. So when you get to query planning, sort of it like when you get to a review and you want to go like to an author, like going through a review to a user or going through, let's say, a post to a user, those are different paths. And
Yeah.
when you start looking at the possible query plans to get to that field, you might end up in like completely different sequence of subgraph calls. So I wonder if there's a way to avoid the complexity of like keeping track of the full subgraph path, but still sort of know when it's relevant.
I mean,
Like for instance, we know for sure that if for instance like take the extreme case, like if a type has a field that leads back to the root, like we would know that that's the same as going directly to the root, right? Because there's no context there that we need to keep track of.
I mean,
And maybe
what if we add the subgraph context to the node, and then essentially, if you think about, we can generate the query path ABC 7 times. We can have the same query path many times. We can the algorithm could actually say that iterate through all the possibilities through all the subgraphs and keep track of the state. Because the thing is that when let's say I'm on subgraph A on the user type, or I'm on the user subgraph, now I traverse to the review subgraph and I traverse back to the user subgraph. This context together with the type and the field that I visit should actually be enough to say that we are now in a loop. When we have the same path back over the same subgraphs, that should be enough, right?
you have the same type. I mean, what you can basically use to detect a loop is like it basically in our case you can simplify it as saying basically you think of which subgraphs can you reach for a given node. And if that set of subgraph names, let's say, decreases, then you're actually not in a loop. But if it increases, you are in a loop. If that does that make sense more? Think about for the API path as you go A, B, C, and suppose A, B, C, you think about all the graph, pass through the subgraphs. And you think about for that type, how many which subgraphs can actually reach with this particular case, right? And maybe it's all of them. But then you go again, you go A, B, C again, you add that on to the open path to get another longer open path. And then it turns out after you do that, actually it lowers by 1, right? In that case, you actually aren't in a loop because you have less options, you have to keep exploring to make sure you can still satisfy further ones. But if the option set expands or stays the same, in that case, you actually aren't in a loop because you have the same options as you had before, and traversing wouldn't get you anymore.
Expanding,
Yes,
how would
yes, yes.
expanding, why do I don't have to traverse more when it's expanding? Because it's still a change in state, right?
Well, it's a change in state. You have more possibilities than you had before to get to that type. And so what that shows is basically you basically went through an iteration of the loop and you ended up with more options. You could just restrict yourself to the options you had before and keep going arbitrarily.
Right. So it is actually a change in state, but it's not a change that we care about because
Right.
right.
Right. That's why
Yeah,
the superset thing and
because we only need to know there's at least one option.
And you do this on type basis. So when I'm on the user field and I have an offer, then I will check how many options I have to traverse to offer. And if I ever reach an offer again, then this should be either equal, there should be equal amount of options, more options or less options.
Yeah. Basically, for each type in the API schema, you can keep track of a list of subgraphs and something to that extent, right? And then you could, imagining tracking that essentially. Yeah, it is per type in the API schema.
Yeah. So I mean, taking a step back, I wonder if there's a way to sort of encode that information
in the path.
In the path without like going through the full query planning, at least in the way we specify this. Because I think it would still be really nice if we could separate those two stages, if we could basically define satisfiability for each individual path.
Right. Like internally, like we do query planning, but to be clear, it's a very simplified version of query planning because we don't actually need to find an optimal path. We just need to prove there's at least one path. So in reality, it's much simpler there, in the validation there specifically. But it's possible that you could merge representations in some sense, so you could actually contain the supergraph information. That's what we're getting at there. But it's possible to do things like that. But it gets a little more complicated in our case, at least in a Apollo Federation, just because there are sometimes things that are path dependent. So or we have features that are somewhat path dependent. So you have to like sometimes expand state, but that's I won't get too much into that because that's complicated.
So follow-up question, right? So as Pascal said, like since we're doing like a mini query planning there, is like should we just refer to section to saying, well, we have to run a query plan against this?
That's what we do in step 2, but we first need to get the paths. So I agree. As soon as we have the paths, we can just say all the paths must be executable, and then we can pass it on to the query planner. But the step 1 it's very important, and it's very good discussion, because if it's subgraph dependent, then this algorithm will be complex enough. But if you think about it, it will be super nice in the specification because it's very abstract and it's 100% correct. Like we generate a finite amount of paths which then are executed. It's very easy to describe. The only thing that we have to figure out is how do we get the open, closed, partial, whatever paths there exist into a format that is describable in the specification without anything that is performance related, right?
Yeah, I think that's probably the trickier part there because we definitely
yeah, go ahead, sorry.
To some extent, we're describing a partial query planning as sort of the other half of this, right? You're able to sort of resume query planning from a node in order to jump to a node. So it's like you're not even necessarily performing whole query planning when you do this. You're sort of piggybacking off that a bit, which is a little confusing. But
it's actually you're generating possible queries, like the passes that you produce. You're generating possible passes through the graph, and then you run the query planner on it in a simplified version.
Yeah.
Yeah, it's good a good way to test your query plan.
Yeah. Could we somehow define cycle detection in terms of like a result from the is satisfiable function that takes in a path? So basically what I'm saying is, could we, as part of generating the paths, like we can either describe this as like first describe like a finite list of paths and then run like satisfiability on each path, or maybe we can actually describe this in sort of in a loop. So when a field is when a path is satisfiable, maybe there's some extra state that's returned from that function that we can then use to decide whether we want to add further fields onto the same path, for instance.
You definitely can't generate all the open paths and then like do query planning afterwards, because in order to detect cycles, you basically need the query planning information is the story, right? So you definitely sort of need to do it as you go along, if that makes sense.
Oh yeah, but I mean, in terms of how we describe this, I'm just trying to see what sort of the minimal information is that we need to pass between query planning and generating the paths.
Yeah.
It still allows us to avoid cycles.
Yeah.
So you do, okay, so that means that without the query planning, we cannot generate the partial paths, the paths.
Well, you won't know what
But we can maybe still describe them separately. So maybe there's basically a loop that generates paths, and as part of that loop, for each path we jump to query planning, and that returns us like just the state we need to decide whether we're in a cycle or not.
That's right. That's right. You could have that happen where basically you just ask query planning every time, and that way you get to sort of not have to think about the whole partial query planning bit. Maybe there's still a bit of it that you might sort of have to pile an open path, but that's a separate thing maybe. But yeah.
It's just a recursive function after all.
Yeah.
Okay,
Awesome.
a lot of information. I probably will also have to look at the implementation of the guild and Wondergraph and everything, satisfiability to see how this is built. Yet, when you look at the implementations, it's always optimized. So that's a bit.
I mean, the core of it's relatively simple, right? It's just like whenever you have, for every possible query you have on an API schema, you can generate some series of subgraph queries that fetches the data. But doing that in practice or proving that in practice is always the hard part. So that's the user implementation dependent part.
So maybe first step is just stating that, and some counterexamples. You know, like here's a few counterexamples of schemas that are not satisfiable.
Right.
Yeah, maybe not even schemas. Could we start the first part? What is a valid path? Like we traverse all valid paths. Well, what is valid path?
Right.
Like,
Yeah.
maybe we just start there.
Yeah. Agree. Because it was also ambiguous in our discussions today. Like what is a path? What is included in the path?
Yeah. It can be confusing.
Okay, let's close the meeting.
It's your moment to send a link to the Apollo documentation where it's exactly written what happened.
I wish. No, it's written in code technically. In code
Code is your document.
Yeah, but okay. I put this on the next agenda again, this topic, and then we dive deeper.
15 minutes again?
Yeah, it says next time. I just wanted
Sounds
to suggest you can propose something else, but okay. See you guys next week.
All right. Thanks a lot.
Thank you. Bye-bye.